Okay, we are going to look at this problem that reads, my young niece was going down the fire pole at a local park. Imagine that she starts her descent and gets to a speed of 1.5 meters per second. She has a grip strength such that she's able to maintain that 1.5 meters per second for a short amount of time. When she's 2.3 meters above the ground, she tightens her grip, causing an acceleration with magnitude 0.46 meters per second squared. Does she stop before she hits the ground? All right, so we're going to look at this problem from the scope of the world and recognize in that analysis that we are dealing with kinematics. And so what are we really curious about here? Well, we're interested in how my niece moves through this situation, particularly the situation of sliding down the fire pole, and we're curious about whether or not she's going to stop in time. And so as we think about the framing of the world and we enter into all of our physics processes, but the kinematics process in thinking about what is the object that I am interested in analyzing. And the object in this case, of course, is my niece. All right, so we're interested in my niece. And now what is it about my niece that we're interested? We're interested in whether she stops in time, right? Whether she hits the ground on time. That's the question. But what is really the framing of that question? Well, it's as she makes this motion of going down the fire pole, and more specifically, if I'm going to figure out if she stops in time, I need to understand that motion in a very specific part of the time that she's going through it. And it really starts, I can answer that question if I think about when I start having enough detail to answer it. It's her motion of stopping that's really going to answer the question. And so when does that stopping start? When does she start to change her motion? Going from down the fire pole to doing something to see if she'll stop in time. And so it really starts when she is 2.3 meters above the ground. That is when the world that I'm trying to analyze comes into focus, right? To answer the ultimate question of does she stop or not. And when does it end? Well, it ends when she stops. Now, as with all problems in physics, it's important to remember that there's other ways to frame this problem. We could say that she is 2.3 meters above the ground. That's how I've identified it. But at that same point in time, she is also tightening her grip. She is starting to slow down. She is changing her motion. You can describe it a lot of different ways. It's the same point in time, however. So how you choose to describe it might actually influence how you analyze it, but that's okay. There's lots of different ways to do it. Same with when she ends. We could look at when she stops. We could look at what does her motion do if she were to make it to the ground, and if she were to make it to the ground, is she still moving? If she were to make it to the ground, is she not moving? Does she ever make it to the ground? So we can answer different questions to solve the problem. Does she stop? So we'll start with this. It's when she's 2.3 meters above the ground, and we stop carrying when she stops. All right, this is all about motion, so we're going to follow the kinematics process. All right, so the first step of that process, of course, was the object. The second is to identify the time that we're going to use, our choices of when we start carrying and when we stop carrying, so that we are able to solve the question that's being asked. We need to next identify the world and the problem within that world. So we do ask ourselves a couple of questions. Is this one-dimensional motion or two-dimensional motion? Is she moving in a single plane, or is she flying through the air like in projectile motion? She's moving in a single plane, so this is in fact one-dimensional motion. And then just for the full kinematics process, we do ask ourselves, do I have more than one object involved? Is this motion related to something else? Are there objects involved? And in this case, there's not. I'm only interested in my niece. Okay, so it's one object, one dimension. Okay, now we truly dive into defining the world, and that means we're going to start with drawing a picture. So here's my niece, here's the pole, and here's the ground. All right. that picture, we define an origin. We choose where position equals 0 in space. And we make that choice kind of based on these initial and finals. We want to make analyzing it, solving it, and the equations easy. And so we often will choose, although not always, but often we will choose that I'm going to set 0 either at the initial condition or at the final condition. Okay? I'm going to set it at the initial condition. So this is my x equals 0 position. Now I know that position is 2.3 meters above the ground. So I also know the position of the ground, which is x equal to minus 2.3 meters. It's negative because it's below 0, right? Anything above 0 is positive. Anything below 0 is negative by convention. And I do, as you know, practice convention. Okay, so the next thing we have to identify is the coordinate system. What plane is the motion in? And it's kind of our normal coordinate system in this case. No rotations necessary. We don't have to think about it being off that traditional Cartesian coordinate system. Okay. Now let's think about what we know. Our variables in a kinematics process that allow us to solve anything about motion. So those are, remember, our initial position, our final position, so the sub f and sub I, our initial velocity, our final velocity, our acceleration and time. These are the same 6 variables we use in every problem, the same 6 I write every single time, okay? Now we choose the numbers that go in here, or maybe we don't know, or we choose what is assumed. Sometimes we have assumptions we can make. So, when does the motion begin? My initial position. Where is the object, my niece, when the motion starts? Well, that is when she's 2.3 meters above the ground, and I've identified that as 0. So her position when she starts, when this motion I care about starts, is 0. Where is she when the motion ends? When she stops? I don't actually know. I don't know where she is. She could be above the ground. She could be below the ground, or the position. She could be at the ground. I don't know. So I put a question mark. What is the velocity when the motion I care about, the motion I'm analyzing, starts? What is the velocity when she is 2.3 meters above the ground? Well, we're told in the problem that the speed at that point is 1.5 meters per second. That's the speed, the magnitude of the velocity in this case. So now I have to be careful, and I want to make sure I identify the direction. Is it positive or is it negative? Well, that depends on which direction she's moving at this point in time. And we're told she's moving down. So because she's moving down, we pop in that negative. So remember, as we're analyzing the world, we're just looking at how fast she's going, but I have to remember that this involves direction. All right. How fast is she going when she stops? Well, that's a known value. She's going 0. If she comes to a stop, she is going 0. All right. No direction necessary. What is her acceleration during this time? It needs to be constant if we're dealing in the world of kinematics, and in Physics 1 we always are, right? So what is, well, calc-based physics you might not be. What is the acceleration during that time? We're told that she accelerates with a magnitude of 0.46 meters per second squared. So again, we're given the number. It's up to us to determine whether or not the direction is positive or negative. So we have to remember how we know whether accelerations are positive or negative. We know that if an object is moving in a certain direction and it's speeding up, so if it's moving in the positive direction and speeding up, that means I'm adding more and more and more and more, and so I have a positive acceleration. If I'm moving in the positive direction and I'm slowing down, that means I'm taking away, and I have a negative acceleration. If I'm moving in the negative direction and I'm speeding up, I'm getting faster, I want to add more to my negative, so I have a negative acceleration. If I'm moving in the negative direction and I'm slowing down, I'm taking away from the negative. I'm slowing it down and I have a positive acceleration. In this case, I'm moving in the negative direction and I am slowing down. So I have to take away from that velocity and I have a positive acceleration. Okay? How much time does all this take? We don't know. So it's a question mark. So here's our list of known values. The next step is to identify which of these variables is going to answer the question that I most care about, the detail. I want to know, the question I'm being asked to answer is, does she stop in time? Does she stop before she hits the ground? Does all of this happen before she gets to negative 2.3? So I can ask the question, when all this happens, where would she end up? Where would she end up if all of that happened? Is it above negative 2.3, in which case she stopped? Or would it be below negative 2.3, which means she's moving when she hits the ground? So we find out her final position. Now, once we know the variable of interest, the thing that's going to give us the detail, we go to our equations. And our equations of motion are x final equals x initial plus v initial times time plus 1/2 at squared. That's one equation of motion. Another one is v final is equal to v initial plus acceleration times time. And the last one is v final squared equals v initial squared plus 2 times the acceleration times our change in position. Okay, so those are the three equations. Which one is going to give me what I want? Well, I want x final. So I'm going to eliminate this one because it doesn't have x final in it. And if I'm going to solve a problem, I want that equation in it, or that variable in it. I could use this one. It solves for x final, but it requires me to have t. And I don't have t. I could get t by using the one I just erased. But let's just see if we can do it in one step. At this one, it doesn't have t, and the only variable it's missing is the one I care about. So this is going to become the equation I use. All right. So now I can look at my list. V final is 0. 0 squared. V initial is negative 1.5, negative 1.5 squared. Plus 2 times my acceleration, 0.46, times delta x, and we know that delta x is x final, which I don't know, minus x initial, which is 0. Now, I appreciate sometimes your teachers want you to manipulate the equation before you solve it, and you can do that too. You can do that too. I like to put the numbers in. I'm a numbers girl. All right, so now I'm going to simplify. I have 0. 1.5 squared is 2.25. Negative goes away because it's squared. Plus 0.92, which is 2 times 0.46, times x final. Nope. I have a problem. We have a problem. X final minus 0. No, we don't have a problem. I feel like we have a problem. Trust the physics, Joe. X final minus 0. So 0.29 times x final. We're fine. We're good. We're perfectly great. Trust the physics. See how you have to tell yourself that sometimes? I got a little distracted for a moment, but I don't know why. Okay, so I move 2.25 over, minus 2.25 equals 0.92 times x final. Okay, so I take my handy-dandy little calculator. I can't use my answer key because I did it differently. So 2.25 divided by 0.92, or negative 2.25 divided by 0.92, is negative 2.44 is equal to x final. So this is what I get out of the equation. Negative 2.44 equals x final. That tells me that when my niece gets to 0, she would be at negative 2.44 meters. So does she stop in time? I still have to interpret the problem. Well, negative 2.3 meters is the ground. If it would take her getting to negative 2.44 meters to stop, she doesn't stop in time. She's moving when she hits the ground, because she would have to get way down here in order to stop. So nope. She does not stop in time. So sometimes we have to remember this, that our answer doesn't actually answer the question. It gets us to the question. We still have to interpret it. And in this case, we interpret it because we know where the ground is. It's at minus 2.3. And if she's going to get to 0, she would have to go to minus 2.4. So she doesn't stop in time. All right. Apologize for that little pause in there. I actually solved the problem different on my answer key, so when I looked down to look at what the number was, it didn't make sense. But we always got to trust the physics. And sometimes, even us experts need to remind ourselves, trust the physics. All right, so there's your process. There's your process for kinematics, practicing it and using it for a one-dimensional motion problem. It involves a lot of interpretation on your part, positives and minuses, so that is always a fun challenge. And that interpretation of the answer, what does this actually mean? Also a fun challenge. All right, good job.